All right, so when we left class on Friday, we were talking about the Diels-Alder reaction, and really, I think I just introduced it briefly. So, Nobel Prize winning chemistry. We looked at the overall reaction where we're taking a 4-membered diene and a 2-membered dienophile, and we're reacting them, and these reactions often don't need any other reagents. They'll actually just kind of go on themselves by heating up the reaction. And you can see that the Diels-Alder cycloaddition results in a 6-membered ring with a double bond, which is a pretty cool reaction because we're making 2 carbon-carbon bonds, and we're also creating a 6-membered ring with a functional group in it that we could do a lot of different things to based upon the addition chemistry that we just learned. All right, we looked at how these 2 molecules have to approach each other or have to interact in order for this reaction to take place, right? And this is a very, very specific interaction, right? Last semester we looked at pi systems and tried to understand how those pi orbitals or p orbitals are overlapping to create these pi systems, right? And so in most Diels-Alder reactions, we're using the HOMO of the diene, and that's reacting with the LUMO of the dienophile. Okay, and just to remind you, when we look at a diene, or when we look at in this case 1,3-butadiene, these would be the molecular orbitals of 1,3-butadiene. Right? There are going to be 4 molecular orbitals based on the fact that we're taking 4 atomic orbitals and overlapping them. Right? And we have 4 electrons, and those 4 electrons are going to be in the bottom 2 orbitals. Okay, so this is what the HOMO looks like, right? The HOMO is going to have a bonding interaction between carbons 1 and 2, bonding interaction between carbon 3 and 4, right? But an anti-bonding interaction, a node between carbon 2 and 3. Okay, and then that's going to be aligned or overlapping with the LUMO of the dienophile, right? Which has an anti-bonding interaction just between those 2 carbons. Okay, and you can see when we get those orbitals lined up the way that they are, they're going to be able to combine in phase, meaning that the shaded part of 1 carbon and then the unshaded part of the other carbons will match up. Right? Now, when I draw these Diels-Alder reactions to show the orbital interactions, I always draw the diene on top and the dienophile on the bottom, and that's really just out of habit. Okay, but you have to realize that the dienophile can also be on top and the diene on the bottom, right? So if I just move the dienophile above, you can see that that same in-phase interaction would take place. Okay. Okay, so this reaction that I've drawn up here doesn't really happen, right? We're not making cyclohexene through Diels-Alder reactions. This is really just shown as an example for the atoms involved in Diels-Alder cycloadditions, right? If we took 1,3-butadiene and ethene and try to get those to react, they probably wouldn't react very well. We probably wouldn't make very much cyclohexene. Right? One compound that does react is cyclopentadiene. All right? And cyclopentadiene is going to react with itself through a Diels-Alder reaction to dimerize. Right? Basically, one molecule of cyclopentadiene is going to react with a second molecule of cyclopentadiene. Right? So see if you can draw the product that would form from the dimerization of cyclopentadiene.
point for this line.
They wouldn't break open. They wouldn't break open. If you're confused about what's going on, right, we're using the molecule as both the diene and the dienophile. Right, so try to line them up this way to predict how that reaction is going to go. If you guys are confused getting started off, remember that the mechanism is always going to be the same. The product that you're making is always going to be the same, and that you're always making a six-membered ring with a double bond. Right? The electron movements, right? We're connecting. These are 1, 2, 3, 4, and then A and B. Right? We're connecting carbon 4 to carbon B, carbon A to carbon 1, and then a new pi bond is forming between carbons 2 and 3. Okay, so 1, 2, 3, 4, A, B. Those are the new double bonds being formed, right? And you can see that the pi electrons are the electrons that are the only ones involved in the mechanism. product coming out. All right, does anybody need more time? Okay. All right, so for these Diels-Alder reactions, at least when you're starting out, it's not a bad idea to draw the mechanism and to make sure you're understanding the carbons that are connecting in this reaction. Right, so mechanism is going to be the same, right? These pi bonds will reach out, make a bond to carbon. These pi bonds will reach out, make a bond to carbon, and then that pi bond shifts over to make a new double-double bond, or a new pi bond. So again, we're always making a 6-membered ring, right? This 6-membered ring in this case is going to be a part of a bridged with a 5-membered ring. Okay, and so this is going to be our product. I can count the carbons, 1, 2, 3, 4, A and B. And you can see that those are the two carbon-carbon bonds that were made. Okay, this is the other 5-membered ring that we added. Okay, and you can see we lost one of the double bonds in that 5-membered ring because it reacted through that Diels-Alder cycloaddition. The other double bond is still okay though, still intact. Any questions about this? Anybody have trouble seeing this? No? Okay, so we can draw this a different way to show that this is a 3-dimensional product. So you can see that part of the original 5-membered ring is kind of sticking up above the 6-membered ring, right? So that would be that central carbon here. And then we also have on carbons A and B, we have hydrogens, right? And carbons 1 and 4, we also have some hydrogens. Right here.
So why would it not just form a 6-membered ring with some more double bonds in it? Like, why does it have to have
Because this carbon's still attached, right? So if it's attached to carbons 1 and 2 in the starting material, and we're not breaking any of those carbon-carbon bonds, it has to be attached to carbons 1 and 4. It still has to be attached to carbons 1 and 4 in the product, right? So the original 5-membered ring. Let's see if I can draw this a little better. So the blue rings were the original 5-membered rings, right? And we're just shifting pi bonds around, right? So we're not breaking rings open with the Diels-Alder reaction. You can see the 6-membered ring that's formed from that cycloaddition though, right?
Yeah, so
Yep.
It's funny. Why would these alkenes react if they don't break anything in the ring?
If they don't break anything?
If they don't break the ring and allow themselves to be on the edge of something, why do they actually reach out and grab the
It's because the orbitals can line up like this. That's ultimately how this reaction works, right? You're overlapping these pi orbitals when these molecules come into contact with each other. And the actual rings don't break because even though the pi electrons are moving, there's still sigma bonds that are holding everything together, right? So this pi bond just reaches out like that, right, which would leave an empty orbital here, which is kind of taken up by this pi bond, right, which would leave an empty orbital there, which is taken up by that pi bond. Okay. So I don't know if that answers your question or not. Okay. Other questions? Yeah, Evan.
On the 5-membered ring of the product,
Yeah.
like one is attached, would that double bond
this one here.
Yeah, would that double bond still be reactive? So would you form another product where you form like another 6 member ring on the other side?
Yeah, so it is still reactive, but it's not going to form another product. And the reason why, so I said that this reaction doesn't happen very well, right? If we take 1,3-butadiene and ethene and try to react those together, it doesn't happen very well. And that's because whenever we do these reactions, the typical way of doing them, the diene needs to be electron rich, so we usually need some electron donating groups. Right? And the dienophyte needs to be electron poor, so we usually need some electron withdrawing group or groups on the dienophyte. Right? And that's really to help out with the orbital. So if we put more electron density into the diene, that's going to increase the energy of the HOMO. Right? If we put more electron withdrawing or make the dienophyte electron poor, that's going to decrease the energy of the LUMO. So it's going to start bringing those orbitals closer together and giving them a better match. And so cyclopentadiene as a dienophile, really the presence of the other alkene that makes one of them a good dienophile. Right, so we kind of think of this as not really a full electron withdrawing group, but something that can help activate the other double bond. And then once we do that reaction, right, that other double bond is not in conjugation anymore, so this won't be as reactive as Right, so this reaction actually happens at room temperature. So if you buy a bottle of cyclopentadiene from Aldrich and you look at it spectroscopically, depending upon how long it's been sitting around, it might all be the dimer, right? Or there might be a combination of the dimer and the monomer. And so to get cyclopentadiene, what you have to do is you have to what's called crack it, right? So you get this, the dimer or whatever's in the bottle at the time, pour it into a round bottom flask, and you just boil it and distill it, and upon heating it, it de-dimerizes, I guess, goes back to just the cyclopentadiene, and this has a lower boiling point than the dimer, so you can just distill it off as it forms, right? And you usually just use it fresh because after a couple of days, it's returned, even at room temperature, it's returned to the dimer. Yeah. So, questions about that? I want to talk about stereochemistry, but we won't do stereochemistry until Wednesday, and we'll also probably start a new chapter in chapter 16 on Wednesday.